Okay, nice. So I'm going to continue from where we left off last time. And we're going to see some more examples of smart contracts today, and also some examples of the common vulnerabilities and the common hacks that happen. So last time we saw a front-running attack. And this was this idea that we had a contract like this, which gave a price to anyone who could basically invert a hash function. So anyone who could provide some particular input, particular parameters to this function could get paid. Now, the problem that we talked about was that suppose you solve this puzzle and suppose you want to claim your reward from the contract. So what you would do is that you would create a transaction that has a function call in it, and that transaction would call claim price and give the right value of X. But when you put this transaction out and you publish it on the network, a miner will see it. Now, normally what a miner should do, if the miner is honest, is that they should just include your transaction into the block. But what would happen in practice, or maybe in theory, if the miner wants to attack you, is that they will just look at this transaction and see, okay, with this particular value of X, I can claim this price. So they can just steal your value of X and create another transaction in which they are the ones who are calling this claim price with this value X. And since this is done by the miner can just put their own transaction before yours, and they can get the prize money here. And this is why it's called front running, because the idea is that, this is a very special case of front running, but generally whenever we say we have a front running attack, what we mean is that someone creates a transaction and someone else can find another transaction based on the information that was in the original transaction, and then they can just front run it, switch the order, and somehow get money out of it or get a higher payoff out of it. This is the most classical example of front running, but generally whenever you write a smart contract in Solidity, for every one of your functions and for every one of the things that you do in your smart contract, you have to make sure that they are not vulnerable to front running. So this is one thing you have to keep in mind. And by the way, last time I had some errors here because of types not matching. So these are the right types now. And I have also put this code on Canvas. Okay. So this is the first thing I wanted to tell you. Now, the second thing I wanted to talk about was about transferring money. So until this point, we have seen one way of transferring money, and it's this one, where you basically just call the transfer function, and you say who's going to receive it. So this receiver is an address, and it should also be payable. And you just say receiver.transfer this amount, which means that send this much money to this receiver. And as we saw before, if an error happens, for example, if you don't have this much money or if something else goes wrong, then the whole transaction will get reverted. But there are also other ways of sending money. And I just wanted to show you some of this. Actually, I can show you using this website. This is a great website, by the way, soliditybyexample.org. So you have the function transfer, where you can basically just send the money. And what happens here is that if the transfer fails, you will just get an exception, which means that then the entire transaction will be reverted. But there is also another function called send. And what this one does is that it returns a Boolean value. So instead of using transfer, you can just use send. And if it's successful, you will get a true value. If it's unsuccessful, you will get a false value. And then you can do whatever you want with that information inside this function. But actually, another version or another way of sending money that is more recommended these days is via a function call. And this is what I want to talk about for a few minutes. So if you look back at this contract that I wrote last time, the way we would pay this contract was using this function called deposits, right? So I basically had a function whose job was to get paid. The idea was that if I want to pay my contract, I just call this function, and this function is payable, so I can include some value. And remember that here, when I was making my function calls, I could add a value, so I could say, for example, send 2 Ether to this contract. Now, generally, this is not a great idea, and it's good enough for simple contracts and contracts that mostly work with, let's say, real-world people. But if you want to have your contract receive money from any other contract, so if you want to be able to receive money from any other contract, then we have to standardize the name of the function that gets the money, right? So I can't just call it whatever I want. I have to have a standard name. And the standard name that we usually have is receive. So you can just have a function called receive, and it's written like this. And of course, this should be an external function, which means that it can only be called from outside of this contract. And of course, it should be payable, which means that people should be able to send some money to you.
What?
Okay, can you mute yourself? I don't know whose voice this is. Okay, so you can have a function called receive, which is external and payable. And basically the idea is that whenever someone sends money to your contract, this function will be called. Okay? And another concept here, which is very similar, is the concept of a fallback function. And okay, I'll get back to that. Let me just say one more word about receive. So one really important point here is that the amount of gas that the receive function can use is limited. So I think in the current versions, the amount is like 2,300 units of gas or something like that. So in your receive function, you cannot really do much, but you can do a small number of things. So for example, you can just have a receive function that gets money from someone and updates the value of, let's say, their balance in your contract. But anyway, the receive function is called every time someone sends money. Now, another thing that I wanted to talk about was generally about calling other contracts. So we saw an example of how you can call another contract, and this was the example. So the idea was that we first put the other contract on the blockchain, and after we put this contract on the blockchain, after we deploy it, it will have an address. So we can use that address to talk about this contract, right? So what we can do is that I can say, take the contract, which is of this type, and is at this particular address, and then call the withdraw function on it. Okay? But, well, this is a special case of a much more general situation, and the general situation is this. It's called call. So here's the thing. What happens if I don't have the code of this contract? So here what I'm doing is that I'm putting both contracts codes into the same file, and I'm compiling them at the same time. So here when I write my contract C, the Solidity compiler knows exactly what kind of contract C is. So it knows that it's a contract of this type and knows exactly what functions C has. But suppose that someone else has written a contract and put it on the blockchain, and maybe you don't have the code of the contract, you only have the bytecode because that's the only thing that is put on the blockchain. And the only thing you know about this contract is its address and that it has a function called deposit. So how would you call such a contract? And this is where we will use the call function. And actually this gets quite complicated, and we don't really use this very often in the real world. I just want you to know that this exists. Okay? And here's the way it works. So you have to use the address of the contract that you want to call, and you write address.call. And then when you make a call, just like here, where you set the gas limit and you set the value, you have to do the same thing here. So you have to say, what is the amount of ethers or cryptocurrency that I'm willing to send to the contract at this address when I'm doing this call, and how much gas I'm willing to pay for this call. So again, this is itself inside another contract, right? So I have a function that is calling a function in another contract. So this function already has a bunch of gas, but it can decide how much of that gas it wants to share in this function call. So you can just say, as I said before, this is the address of the contract that I want to call. This is the amount of money that I want to send with my call. This is the amount of gas that I'm willing to pay with my call. And then here's the part where it gets a bit more interesting. You have to say which function you want to call in that contract. And the way that you do this is that you first say, okay, I want to call a function, for example, called foo. And this is how that function looks like. It gets a string and an unsigned integer. And well, here we have the code, so you can see that that function actually exists. But even if you didn't have the code of that contract, as long as you just knew the function header, you could do this. And then you say, okay, when I want to call this function, and these are the parameters. So for example, for this string, I want to pass call foo, and for the integer, I want to pass 1, 2, 3. But another point here is that all of this information has to be converted into a very specific format. So because we want to have some space savings on the blockchain, so it's not actually that all of these strings go up there, it will be in a binary format. And you have ways of converting to that binary format, and it's like ABI.encode with signature. So anyway, my point here is quite simple. You can call functions of other contracts even if you don't have the code of those contracts, as long as they're on the blockchain and you know the name of the function and so on, you can call the functions. But now, as you saw here, if I just have a contract like this that has a call to another contract, when I compile this contract, my compiler does not have access to the other contract that I'm calling, right? Because maybe the other contract is just on the blockchain. So the way this is compiled is without any kind of check that this function actually exists and I have the right header and so on, right? So every contract is kind of compiled separately. And this is similar to how, for example, the external parts of codes or externs are compiled in C++. So what happens if I write the contract, if I write the function name incorrectly? So suppose that I say, take the contract at this particular address and call the deposit function. So let's say I've put this contract up and I say I want to call the deposit function. But suppose that, for example, I have a typo. So instead of deposit, maybe I write it with 2 T's. So that function doesn't exist, right? So this is the role of the fallback function. So whenever I have a contract, if someone makes a call to a function that does not exist, or if someone makes a call to a function but gives me nonsensical parameters, for example, this function needs an address as its parameter. Suppose that someone calls f, but gives me a bunch of data that cannot really be converted to an address. Then in these cases, the fallback function will be called. Okay. And again, you can make the fallback function payable, which means that if someone made a wrong call and paid you some money, you're going to collect it anyway. But another case where the fallback will be called is if you don't have a receive function and someone sends you some money. So as I said before, if someone transfers some money to you, that will trigger your receive function. But if you don't have a receive function, that will of course trigger the fallback function. So in practice, you will see that many of the real world smart contracts don't really have a receive function and they just use fallback. And by the way, if you don't have fallback, which was one of the problems that I had last session, and I was too sleepy to figure it out, was that, okay, if you don't have fallback, you cannot send money to this contract, right? Because if my contract just looks like this, there are no payable functions here in Alice's contract, so no other contract or no other person can send money to this contract. So I actually need to have the fallback for that. Okay. Great. So now another thing that I want to tell you about, this is again not that much of an important thing, but we can also have what's called events in our Solidity smart contract. And events are basically a way for you to do debugging when you're writing the code, and also a way for you to write logs when the code is actually deployed on the blockchain. So the way this works is like this. So suppose I have this contract. It has, as we see here, two addresses, Alice and Bob. It has a function called setAlice, which sets the address of Alice to whatever address we give it. And so maybe I want to also write a log every time this happens. So what I can do is that I can say I have an event, and let's give this event a name. So let's call it, for example, change of Alice. And I have to say what kind of information I want to put in the log when this event happens. So maybe I want to have an address which was the address of the old Alice, and another address which is the address of new Alice. Okay. So you can just think of this event as a way of writing logs on the blockchain. Okay. Now, what I do here is that I'm changing Alice to A, right? So I can just create an event, which is called change of Alice. And I can say that, okay, I have to do it before this. I can say that the old value of Alice was, well, Alice, and the new value is going to be A. And the way that I actually trigger the event is using the keyword emit. Okay. So let's see what happens now. I deploy my contract. And the log is here. So the deployment was successful. Now I have my contract here. Let's say I want to set Alice to one of these accounts, for example, to this one. So I copy the address here and I do set Alice. Now, this was also successful, but if you look at the log here, okay, you can see in the log that there was a change of Alice event, and these are the arguments for that event. So the old Alice was this, and the new Alice is this. Okay, so this is a really nice way of writing logs and being able to debug and see what's happening with your contract. But you can also have this in your contract when you actually put it on the blockchain. And what would happen in that case is that since everyone on the blockchain has consensus about every piece of code that is being executed, so everyone will also have consensus about the events. And you can, for example, have an app that just listens for some particular events. So suppose that you want your app to do something when some particular event is triggered in your contract, you can just listen for that event and see when it happens on the blockchain. Okay. So let me see. There is a question here. Is it possible to set the fallback to another contract? Yes, you can. Basically, in your fallback function, you can do whatever you can do in any other function. The only difference is that there is a limit on how much gas the fallback function can use. So, yes, that's the only limitation here. And actually, hopefully today we will see an example of how this can cause a bunch of problems. So based on this, I want to just go ahead and do another example for you where we implement a very simple smart contract, and then I'm going to show you how things can go wrong. And actually, I will show you one example of using the fallback function to attack another contract. Okay. So there is a question, will the caller of set Alice need to pay extra gas for storing the new entry in the events log? Yes. So you have to basically emitting an event and so on, all of these things will be translated to bytecode, and each bytecode operation has some associated amount of gas that will be used. So you will have to pay gas for emitting events. But okay, one important point is that generally your contracts have access to almost all the information that is written on the blockchain. And we have seen this before. For example, we saw that the contract can check the balance of a particular person or another particular contract. We also saw that you can get information about blocks. So you can get, for example, the address of the miner of a block, you can get the hash of a block, you can get the timestamps of a block and so on in your contracts. But the crucial difference is that the contracts do not have access to events. So if you write an event, you cannot have another contract that just reads the events. Okay. So let me create another contract here. So let's call this one bank. What I want to do here is that I want to implement a very simple bank where people can deposit their Ethereum and they can also transfer it. Now, this is not a very useful thing in practice because, well, you can just transfer your Ethereum on the blockchain directly. You don't really need a smart contract for it. But the use case of these kinds of contracts is to create new tokens or new currencies. So suppose that you want to create your own coin, you can do it like this, and then you can basically have a smart contract on the Ethereum blockchain in which you keep track of this new coin that you have created and you can transfer it and so on. Okay, so let's start. And as usual, we have to first say what version of Solidity we're going to use. Go to the compiler here. Okay. And then we can have a contract. Let's call it bank. Now, what I want to do in this contract is that I want to allow anyone to deposit money. And I also want to allow people to transfer money between their accounts. Okay. So the first thing that I will need to do is that I need to keep track of everyone's account. And a very handy thing for this is to use a mapping. So I can have a mapping of addresses to unsigned integer, which I can call balance or account balance. And the idea is that the account balance of each address, of each individual, will tell me how many tokens or how many units of currency they have in their account. Okay. Now, again, I'm not going to use a token other than Ethereum itself. So I'm actually going to have a bank where people can deposit and transfer Ethereum, transfer Ether, sorry. So, okay. Now, as we had in this previous contract, we can just have a deposit function. So I can have a function deposit, which is public and payable because people should be able to pay it. And what I want to happen here is that I just want to say the account balance of the person who's paying this money, which would be msg.sender, should be increased by the value of the money that was sent. So that's msg.value. So writing a deposit function is super easy, but as I said before, I don't like to have this function named deposit. I would much rather have a function called receive, or actually I would rather just have it as fallback, right? And fallback should be external. So this means that anyone can just send money to this contract, and now by default, the fallback function will be called. So whenever someone sends money, their account balance increases. Okay. So this was easy. Now, the next thing that I want to implement is that I want to let people transfer money inside this contract. So suppose that Alice wants to send some money to Bob. I want Alice to be able to just call this contract and send the money. So let's say I have a function and I can call this one transfer. And this function is of course public because everyone can call it. It's not payable. And so when you call a transfer function, you can think of this as a bank transfer. You have to give the address of the recipient, and you have to also give the value that you want to send. Okay. Now, as I said before, I want this address to also be not payable. No, sorry. In this case, I don't want to do that. I'm going to do the transfer only by changing the account balance that I have here for the recipient. Okay. So I would first require that the sender has enough money. So actually, let's write this down. So whose sender? Sender is msg.sender, and the value is of course this. And I can just have an unsigned integer called sender's balance or sender balance, which is the account balance of the sender. Okay. And let's say I also take the recipient balance, the account balance of the recipient. And so I have to first require that the sender has enough money. So I would just require that sender balance is at least the value that I have. And by the way, in your require, you can also add an error message. And this error message will be written in the log if this require fails. Okay. So what this means here is that if the sender balance is not more than the value, I will just get an error that tells me not enough money. Okay. Now, what do I do next? Well, just decrease the sender balance by value, increase the recipient balance by value, and write it back into this account balance. Okay. Balance of recipients. Okay. So, this is, for example, how I can write the transfer. And of course, I could write it in a much shorter way, but the reason that I wrote it like this is to show you what can go wrong. So can you see why this is not okay? Can you detect the bug that I have here? So let's do something. Let's say that these account balances are public, and let's actually deploy this contract. So I deploy my bank contract. Okay, actually, let me also have a function called deposit. I'm adding this because it's just easier here in the virtual machine to call that, which is public and payable. And what it does is the same as the fallback. So it just increases my account balance. So let me deploy this. Now I have this bank. And let's say I use this very last account here. And I deposit, let's say 12 Ether. 12 Ether deposits. Okay, this was successful. So now I can look at the account balance of this account, which is basically just a number in my contract. So I check the account balance and it's 12. And this is because the unit of currency in Ethereum is not actually Ether. It's this smaller thing. I think it's called VEI. But yeah, so I have 12 Ether here. Now, I want to have a situation where I get free money. What can I do? So consider this function transfer. What does this function do? It takes a bunch of money from one account and puts it in another account, right? But what happens if the sender and the recipient are the same? So suppose that using this account, I say that I want to transfer to myself and I want to transfer all the money that I have. Okay. So I call transfer. And of course, this works. I had to, of course, pay some gas for it, but that doesn't matter. Now I check my account balance again. And you see my account balance is now 24 Ether. I can do the transfer several times, and then I can check my account balance, and it's increasing every time I do a transfer. So this was a very simple bug. The bug is that if the recipient is the same as the sender, what we're doing here in this order is actually incorrect, because I'm first taking the balance out, putting it into this variable, and then I'm doing the increase and decrease on this variable, and then I'm writing back the balances, right? So this opens the door to this kind of bug where someone can basically create free money for themselves. Now, so how can we fix this? Well, we can do a bunch of things. For example, I can say here that I require the recipient to be different from the sender. Okay, that's one way to fix this. Another way is to just write this in a much simpler way and not store these balances into different variables and just directly work with the mapping that we have here. But anyway, so here I'm just going to add another require, which says require sender is not the same as recipient. And if so, just say can't send money to yourself. Now, why did I show you this really simple and stupid example? I did this because I wanted to show you that it's really important to verify the correctness of your smart contracts, because it's very simple that you make some errors that you might not even think about. So if you consider this simple code that I wrote here, maybe I would write it like this, and it doesn't even occur to me that what happens if someone sends money to themselves. But the problem here is, of course, that they can steal money. Now, later on in this course, we will see some examples of tools that you can use for automatic formal verification, so that they take the code of your contract and try to tell you if something is wrong. Okay, I don't know why this becomes like that. Recipient. Okay. Now, great. So someone is asking, will this contract be suspended in getting uploaded to the blockchain because it creates a new unit of currency? It actually doesn't create a new unit of currency, because here's the thing. The error that I have here, when I say it creates money out of thin air, well, I'm just thinking about this account balance that I'm saving here in this contract, right? So I'm not really thinking about what's happening in the blockchain. On the blockchain, what happens is that this contract owns a bunch of money, and if I can have a transfer like this, it's equivalent to being able to steal that money from this contract. And actually, let me write the withdraw function so that we can talk about this more concretely. So suppose that I also have a function called withdraw, and let's say this function is also public, and this can be used to withdraw the funds. And again, I can have a situation where I give this function, I tell this function how much money I want to withdraw, or I can just have a simple withdraw function that gives me all of my money back. So I will just have to say, let's say I have an address payable recipient who is now msg.standard. I have to convert it to payable explicitly. And then I just say recipient.transfer. Now, how much money do I want to transfer to them? I want to transfer their account balance. So account balance of recipient. And of course, I want to set the account balance to 0. Okay? So suppose that I have a withdraw function like this. When I said I can create money out of thin air, what I meant was that I can actually steal money from this bank contract. So let me show you an example of how that would work. So let's say I deploy this contract, and let's say I deposit some money. So with this account, I'm depositing 5 Ether. Right, so if I now check the balance of this account is 5 Ether. Okay. Now I switch my accounts, and with another account, I send 1 Ether to the contract. So I deposited 1 Ether, it went through. I copy this and I check this account balance, and it's 1 Ether. Now, what I want ideally is that since with this account I have only given the contract 1 Ether, I have to be able to withdraw only 1 Ether, right? But what's happening on the blockchain? On the blockchain, this contract now holds 6 Ether overall, right? So if I can somehow trick this contract to pay me more than my 1 Ether, this contract is actually able to pay me up to 6 Ether. So, and that's what I'm going to do. I'm going to transfer 1 Ether to myself. So I have to give this first, and then 1 Ether. Oh, okay. So I forgot to remove this require. I have to now do the whole thing again. Okay, let's say you can't send money to yourself, just so that I show this tag. Okay, so I deploy it. I deposit 5 Ether. Then I go to another account. I deposit 1 Ether, and now my account balance is 1 Ether, but this contract owns 6 Ether on the blockchain. So now what I do is that I transfer 1 Ether to myself in the contract. So the names are a bit ambiguous here. I'm sorry about that. I shouldn't have called this transfer, because you might think that this is actually a transfer on the blockchain, but it's not. It's a call to the function transfer. Okay, so now I transfer 1 Ether to myself, and because of the bug, because of the vulnerability that I had, if I now check my account balance, I see that my account balance is 2 Ether. Now, what is the problem? The problem here is that the contract on the blockchain holds 6 Ether. And now my account balance has become 2 Ether. So if I call withdraw, the contract will pay me 2 Ether. And as you see here, I got 2 Ether out of the contract. So now that other person who had paid 5 Ether to the contract, this guy, cannot withdraw his money, because the contract now has only 4 Ether, but the balance of this guy was 5 Ether. So if he tries to withdraw it, the contract does not have enough money to pay him here. So basically what happened here is that because of this bug, I could steal 1 Ether from this contract. And again, no units of currency actually get created on the blockchain, because the blockchain protocol actually keeps track of which contracts own how much money and does not allow this contract to spend more money than it has. But actually, if you think of this contract as a bank where you can deposit and withdraw money, as a customer of this bank, you could create new units for yourself, which was basically the same as stealing banks' money. Okay. So let's go back here and let's say we require that the recipient is not the same as the sender as before. You can send money to yourself. And this was to avoid creating money out of thin air. Okay. But now our contract has another big problem. Let's see. Okay, I don't want to talk about this one. I want to talk about this one. Okay. So I talked about what happens when a contract sends money over to another contract, right? So when I send money over to another contract, I'm going to call its fallback function. So let's look at our bank contract. What our bank contract does is that it transfers money to the recipient, okay? And actually, I can do it using transfer or I can do it using send. It doesn't really matter for this particular example that I want. I mean, it gives you a warning that what happens if send fails, you're not checking the return value and so on, but anyway, it compiles. Now, as I said before, on the Ethereum blockchain and on almost all other programmable blockchains, each account can either be a contract or it can be a public key that actually has a corresponding private key and is under the control of a real-world person. So when I have an address here, this address can actually point to another contract. So let's see what I can do. Let's say I deploy my bank contract just so that I have it there. And let's say I deposit 10 Ether into my bank. Okay. So the bank contract now has 10 Ether. Now I'm changing my account again. Okay. Now I want to write another contract. And I'm going to call this contract attacker because later on we will see that I want to use it to attack the bank contract. And what I'm going to do here is that I'm going to basically create an account, but create an account for this attacker contract. So here are some functions. So let's say I have a function called deposit here, which is public and payable, and doesn't do anything. So I can just pay some money to my attacker contract now. And okay, let's say that I also have another function, which is called, let's say, create bank account. And this function is also public. And what this function does is that it calls the bank contract. Okay. So in order to call the bank contract, as we saw here before, I actually need the address of the bank contract. Okay. So here I'm going to say that this create bank account takes the address of the bank contract. Okay. And calling it is exactly as before. So I will have something like this. So I have to write bank, let's call it my bank, is bank at that particular address. So it's a bank at this address that was given to me. Okay, this payable, just to avoid that error. Okay. Now, and what I do is that I just call my bank dot deposit. So I deposit something in my bank. And how much do I want to deposit? Well, I can just look at my own account balance, or I can just have some amount that I deposit, or actually I can even put all of this together. But anyway, so let's say I deposit 1 Ether, and okay, what would we write 1 Ether? Okay, I think it was, yeah, okay. Okay, let me just use the fallback function. So let's say I just, I just transfer some amount of money, 1 Ether, to my bank. Okay. I have to write Ether. Okay, again, I'm not used to this new version of. So okay, I can just say how much I try. Yeah. Yeah, I make this problem every time. So the problem is that I shouldn't have called this transfer. So let's call this one transfer money. And let's call this one withdraw money. And let's call this one deposit money. Okay. So I want to make sure that the fallback function is called. So here I would just say my bank, or actually I can just use it. Yeah, I don't even need to call a function of the bank. I can just use the address. So I can say this address, the transfer 1 Ether. Sorry, I just for a second confused the library function transfer with the transfer function in my bank. Okay. So the way I can create a bank account was simply to send money to my bank contract, right? Because the fallback function would just increase my account balance. So I don't need to actually call any of the functions there. I can just send the money to my bank. Okay. So what create bank account does is that it creates a bank account, but it creates the account for this contract. So this contract, the attacker contract, has an address, and we will have a bank account with this address. And that bank account will have 1 Ether. Of course, this is assuming that the attacker contract had 1 Ether to send. Okay. So now what's the problem? The problem here is that what happens if I withdraw? What happens if I want to withdraw my money? So let's do this. I create a function for withdrawing in my attacker. So I call this one withdraw my money. And as usual, I will just have to have the address of the bank contract, and it's public, this function. And I just have a bank, which is the bank at that particular address. And I will just call the withdraw function, so the withdraw money function of my bank. Okay. So now I have a contract that is working with the bank as if it's a real person. It's creating a bank account, putting money in that bank account, and then withdrawing money from that bank account. Okay. Now, let's just deploy these things and see that they actually work, but then I will come back and do the attack. So I first deploy my bank. Okay, now let me change my account, and let's say I deploy now the attacker contract. And I pay some money to the attacker contract. So let's say I pay 2 Ether to the attacker contract. Okay. Now the attacker contract has 2 Ether, so it can create a bank account that has 1 Ether in it, right? So I can call create bank account, and I need the address of the bank. So I just put the address of the bank here, and I call create bank account. Okay, something went wrong. Okay. I'm not sure again what went wrong here. This happens all the time when I'm writing smart contracts. Okay, so let's actually use deposit money instead here so that we don't have this error. Okay. So I'm going to have a similar situation as before. I just create address, and now I have to call this deposit money. So I would say my bank that's deposit money. But when I do this call, since it's payable, I want to also send some money. So I think this was how we would do it. I would just say value 1 Ether. Yes. So this basically means that I'm calling the deposit money function in my bank, but this call also has a value of 1 Ether. So I'm also sending 1 Ether worth of money when I'm calling this deposit money function. Okay, let's see if this works. I really hope it does, because what I want to show you is not really dependent on this. Okay, I deployed the wrong contract. Let me first deploy bank. So this is the bank. And now let me deploy the attacker contract. Okay, so this is the attacker contract. And let me deposit, who knows, let's say 2 Ether into my attacker contract. So my attacker now has 2 Ether. And now I want to create a bank account. So I just have to give the address of the bank and call create bank account. Okay, this worked. So now the attacker contract has an account with the bank contract, and that account has a balance of 1 Ether, right? So I can just copy the address of my attacker, and I can check its account balance. And as you see, it has 1 Ether in the bank. Okay. Now, the problem that we have here is what happens when the attacker wants to withdraw the money. So let's actually try to do this. Let's say the attacker says, I want to withdraw my money from the bank. So I try to withdraw. And so when I do withdraw, the bank is going to send me my money. Right. Now, when the bank sends me the money, what we said was that I can have a function called receive in my attacker contract, or I can have a function called, let's say, fallback, which will be executed whenever someone sends me money. So I can have a fallback function, right? So if I have a fallback function here, and it has to be external payable, when I withdraw my money, the bank sends me the money, and by definition, when the money is sent to this contract, this attacker contract, the fallback function of the attacker will be called. Now, normally this wouldn't be a problem, but the attacker can actually write some extra malicious code in the fallback. So here's what I can do in my fallback. I can say I want to withdraw money again, right? So I can just say, actually, let me put this bank contract address up here. Let me have a function just called setBank. Okay, so I don't want to just pass this as argument every time. I just want to set it once, I'm able to work with it. Okay. So in my fallback, what I can do is that I can call the bank again. So I can say my bank is again a bank at this contract address. Actually, I can even put this here. So I don't know, I've been coding with a much older version of Solidity, so almost nothing works for me now. Okay, anyway, so what I can do in my fallback function is that I can call my bank again. So I can again have this, and I can call it again. Okay. Now, why is this a problem? This is a problem because, well, with this attacker contract, I can now pay 1 Ether to my bank, and then I can call withdraw money. What would happen here is that the bank will check, okay, my account balance is 1 Ether, so it will send me 1 Ether. But before it sets my account balance to 0, because this send function calls my fallback function, I will make another call to withdraw money. And so I will get back here and it will send me another 1 Ether. But still my balance is not set to 0, right? It sends me the 1 Ether, and again, the send calls my fallback function. So this goes on forever. Of course, this is not a successful attack because it goes on forever, but instead I can just make sure that it goes on for maybe twice or 3 times or any number of times that I want. So I can just have a counter here, which tells me how many times I have try to withdraw money. And I can say, set this counter, just increase this counter. And if the counter is, for example, less than 5, do this, otherwise don't do it. Okay, so I can, for example, say that I want to withdraw money 5 times. Right. So now what happens is that I pay the bank 1 Ether, but I can withdraw 5 Ether from the bank. Or I can withdraw any other number. I can just choose whatever number I want here. Of course, I have to be sure that I have enough gas to do all the withdrawals. So yeah, let's say I want to do it twice. Okay, or maybe let's set it to 3, whatever. Now, let's see if I can actually successfully run this attack on the virtual machine. I hope that I can. Okay, so let's create a new account here. And let's first deploy the bank. Okay, so I have my bank now. And let's say I'm paying the bank 50 Ether. So I deposited 50 Ether. And now let's say I change my account. So now I'm the attacker. I write this contract, the attacker contract, and I deploy it. Okay, so I have the attacker contract on. And I want to first create, okay, I have to first set the bank. So I set my bank to be this bank contract that I have here. And then I will create a bank account. Okay, what happened here? Oh, sorry, I had forgotten to actually pay the attacker contract. Oh, okay. Let's do this again. So I create my attacker contract, and let me also have a function called deposit here. Just public and payable. Okay, so now I deploy my attacker contract. This worked. Now I deposit some money into my attacker contract. So let's say I deposit 2 Ether into my attacker contract. And now then I set the bank. So I tell my attacker contract that the bank is the contract at this address. Okay, this is working. And then I say create a bank account. And as we see here, it was hard-coded that I create a bank account with 1 Ether. So in my bank, if I now ask what is the balance of the attacker, the balance of the attacker is 1 Ether. Okay? And now I call withdraw my money. Yes, it worked. Okay. Now, if I check the account balance of the attacker, you see that the account balance is 0. But what you don't see is that the money was withdrawn several times. So now if I go back to this previous guy who had paid the bank a lot of money and I want to withdraw, oops, okay. Something is wrong here. Actually, what is my account balance here? Oh, okay, I'm using the wrong account. Okay, I lost the account that I initially used. Okay, it was this one, right? What is my account balance? Yeah, anyway, I'm really awful at running examples. But generally, you get my point. So someone else had already paid this bank the money. And basically, the attacker contract could withdraw 3 times instead of once. And now the bank does not have enough money to pay the others. So others cannot all withdraw their money. And This is an attack that is called a reentrancy attack. And it's called this because basically I can use this send, and after I use the send, the fallback function in the other contract in the attacker can call my original function again, and it can re-enter my original function. And this is what causes the vulnerability. So how can we fix this? Well, there are several ways you can fix this, making sure that you don't have a situation like this. Well, one way to do it is to, well, in this particular case, just update the account balance before sending the money, right? So just have some, let's say, amount, which is the account balance of the recipient, and update the account balance first, and after you update the account balance, then send the money over. If you do this, it doesn't matter if reentrancy happens, this fallback function can call your withdraw again, but when that happens, the balance is already zero, so you will not send an extra amount of money. Actually, here it should be the amount. So you first take out the account balance, set it to zero, and only after you set it to zero, you send the money over. Okay? This is one simple way of fixing it. Another simple way is that you can just keep track of whether this function is already being executed. So I can just have some integer, and I can call it, for example, number of calls, like how many times was this withdraw money called. And at the beginning of my function, I can increase the number of calls. And then I can say if the number of calls is more than one, so if someone is using reentrancy and calling me again, just do something here. So for example, maybe just throw an exception or cancel everything. Or maybe I can just say require that the number of calls is at most one. Okay, and of course at the end here I have to set calls back. Okay, so I just keep track of how many times this withdraw money is being called, and if I figure out that actually this is the second nested call to this withdraw money, then I would just throw an error. So I require that you cannot have reentrancy. This is another way that you can defend against a reentrancy attack. Okay. So these were the two attacks that I wanted to show you today. And again, sorry that the example didn't work that well. I will again put the codes on canvas for you to see. But generally, you have to think about a lot of weird things that can happen on the blockchain. So when you write your code, you have to know about a lot of vulnerabilities. We will see even more examples of this. You have to always read your code very carefully, check that you don't have any of these common vulnerabilities. You have to usually ask someone else to also do the checking. This is usually called a security audit. So there are actually companies that specialize in this, in checking the codes of your contract for particular security vulnerabilities. And there is also some automated tools that we will see in the next sessions that can be used to tell you if you have these kinds of errors. I'm going to now answer the questions in the chat. Okay. So another question in the chat is it possible for the compiler to check if a particular function actually exists in a reference contract or even during deployment? Well, so here's the thing. Your compiler is a local thing, right? Your compiler is a program on your own machine that turns Solidity code to the EVM bytecode format. Now, the problem with this is that since it's a local thing, it doesn't really have access to the whole blockchain. So you don't want it actually to have access to the blockchain. You don't want your compiler to be based on the current state of the blockchain, because the role of the compiler is to just translate from one language to another language. So the compiler cannot check if a particular function exists in a reference contract. Here, what we do is that we call other functions like this, which is basically telling my compiler, hey, I think the contract at this address is a contract of this type, and this is the code that I expect there. So this helps the compiler to give you errors if you, for example, call a function that doesn't exist. But in general, if you use this call primitive, the contract cannot know if the function that you are calling actually exists. And that's why actually we need the fallback function, because you can have a contract that calls a non-existent function of another contract. And then everyone on the blockchain should be able to reach a consensus about what happens in this case. And the rule is that you just call the fallback function. Okay. So another question is, based on the error before with the transfer function, can we make our own custom function with the same name as the built-in functions? Yes, and that's actually the really terrible idea that I had here, and I also created a function that was called transfer. It's not a good idea. It will override the original function, and it makes everything complicated, and actually in this case it just confused me, so I would rather not do it. So another question is, can we call withdraw money inside the fallback? Yes, we can. Basically, in the fallback function, you can do whatever you can do in any other function. This is just a function. So you can write any kind of command that you like in here. As I said before, there is a limit on how much gas you can use, but that's the only limitation. Okay, another question is, what if send fails? Okay, so it depends how you actually send the money. So you can actually look at this webpage for some examples of the different types that different ways that we can send money to a smart contract. So if you use transfer to send the money and it fails, it will just throw an error. And you can also have try and catch and things like that, where you can do error handling in your contracts. But if you don't do error handling and there is an error, the transaction will just get reverted. So that's what happens with transfer. With send, what happens is that if it fails, it returns false. So if you're using send, you have to just check the return code and see what happened. And call also just returns a Boolean that tells you whether the function call was successful or not. So another question is, we don't need to set the initial value of those variables. In general, all variables are always initialized to 0. We have to also have a rule for initialization, because again, this goes back to the idea that everyone on the blockchain should reach consensus about the state of every contract. So we have to have a rule about initial values, and the simplest rule is to have everything equal to 0, and that's what Ethereum does. So another question is, so in the reentrancy attack, the line of code following recipient.send will only be called after the attacker runs out of gas. It's a bit more complicated than that. So I will talk about out of gas exceptions and what happens exactly when gas runs out in a future session. But here, what I want to do as the attacker is that I actually don't want to run out of gas. So I will set this number so that I withdraw as much money as I want to withdraw without actually causing any further errors. So that's why I, for example, set the counter to be at most 3 here. So I want to withdraw 3 times. Okay. Another question is, won't this allow concurrent call of withdraw function from 2 different entities? Generally, we don't have concurrency. And well, it's I have to be more specific. We have concurrency in the sense that two different people can create transactions that call functions of the same contract, or maybe even the same function, and they can concurrently publish these transactions at almost the same time on the blockchain. But we don't have concurrency in the execution, in the sense that whenever a miner creates a block, they have to decide which transactions they put in their block. And they have to also decide about the order of transactions that go into the block. And then these transactions will be run in order from the first to the last. So actually the final execution will be sequential, and we don't have concurrent calls. Now here, the way this number of calls thing works is that I'm basically calling how many times I have withdrawn money recursively on my stack, right? So number of calls is initially 0. As soon as I call withdraw money, number of calls becomes 1. But then at the end of this function, number of calls again becomes 0. Okay? So the only thing that number of calls checks is that I don't have reentrancy. So if I get here and I send some money, let's say, to the attacker, and if the attacker's fallback function or the attacker's receive function calls back into withdraw money, then the number of calls here will become 2, and then I will know that I'm having reentrancy and I will cancel the transaction. Okay, and yeah, just one more point that I want to say here, as one of the questions mentioned, sending this money can fail. And this is an example that we actually saw last time as well. So if the recipient is not able to receive any money, for example, if the recipient is a contract and it has no payable functions, so you can't actually send the money to it, then this send here will fail. And so in the real world contracts, if you are actually implementing something like this on the blockchain, you have to check the return value of send, you have to do error handling and things like that to make sure that if this money didn't actually go through and wasn't actually sent, you don't change the balance of the recipients. Okay. Any other questions? Great. So I just want to mention one more thing about the homework that you have to submit. So about the programming homework, some of you have already emailed me and asked about the version of Solidity that you should use. Generally, to make it easier for you, we will run your contracts in Remix, and you can just tell us which version you use, and we will use the same version. So just tell us which compiler version you used. Okay, so another question here is, in exercise 2 of homeworks 4 and 5, can we assume that the auction has an honest owner? No. Okay. Generally, I want you to write it in a trustless way. Try to write it in a way that uses as little trust as possible. I don't want to trust anyone. So we have this auction on the blockchain, and actually we only want the result of the auction to be seen on the blockchain. Whether the actual item is delivered or not, that's a different problem. So you don't have to address that, but you have to address the idea that the contract should work, and the contract should show everyone who has won the auction, no matter how many malicious parties we have. So even if the person who's deploying the contract is malicious, the contract should work correctly. Okay, it's for the point of guaranteeing that the highest bid actually pays. Okay, try to find a way to guarantee this using code. Don't rely on a trusted third party to do this. Okay, great. So another question here is, in exercise 2, do we need to handle the situation of having more than one winner? Okay, that's not really an interesting corner case. So no, it's fine. Just assume that you will not have more than one winner. I hadn't thought about that actually. Nice point. Okay, any other questions? Great. So I'll see you in the next session, and we will see some more examples of things that can go wrong and security vulnerabilities that we can have in our smart contracts. Bye.